Okay. All right, so we almost made it, and I'm glad you're all still here. And so now the last but certainly also a very important session. And so we started with Jeong-Hyuck Park, and so I know him for a very, very long time because we did our PhD together a long time ago. And so he's going to tell us about Einstein double field equations. So please, Jeong.
Okay. To start, I'd like to join all the previous speakers by thanking Joanna for the organization of this wunderbar conference. I'm also joining some speakers by apologizing to give a non-holographic talk. My side will be gravity. Needless to say, general relativity is based on Riemannian geometry, where the only geometric and gravitational field is the Riemannian metric. Other fields are then meant to be extra matter. On the other hand, string theory suggests to us to put a two-form gauge potential B field and a scalar dilaton phi on an equal footing along with the metric. They form the closed string metric sector, and they are ubiquitous in all string theories. This well-known effective action secretly hides ODD symmetry of T-duality, which transforms GB phi into one another. So the T-duality may hint at a natural extension of general relativity, where the entire closed string metric sector constitutes the fundamental gravitational multiplet, and this action then corresponds to a sort of pure gravity. Double field theory, or DFT, initiated by Siegel, also independently by Hall and Zwiebach, turns out to provide a concrete realization for this idea of stringy gravity by manifesting ODD T-duality. So my talk today sketches the geometric construction of stringy gravity. In particular, I will introduce Einstein double field equation as the unifying single expression for all the equation motion of the closed string metric sector GB phi, plus Newton-Cartan, Carroll, and Gomis-Ogre gravities. So this work is done in collaboration with Stephen Angus and Kyung-Ho Cho in Seoul. So it's a bit dull, but it's crucial to set up the notation. We have three groups, ODD, and two-fold spin groups, 1, D-1 and D-1, 1. The opposite signature is a convention, but it's a very useful one. It removes many minus signs. All the capital letters will be always ODD vector indices. And small letters are for the spin group indices. Unbarred are for the one spin group, and barred are for the other spin group. As usual, Romans are for the vector, Greeks are for the spinor. There are corresponding metric in the sense that they can raise and lower the indices freely. So we have ODD invariant metric in this block of diagonal form. So one is D by D identity matrix here. We have two D-dimensional Minkowskian metric, mostly plus eta, mostly minus eta bar. So there are two sets of gamma matrices, gamma and gamma bar, and two charge conjugation matrices, C and C bar. Each symmetry rotates its own indices exclusively. So a priori, a spinor will be ODD singlet. The constant ODD metric decomposes the doubled coordinate into two parts. So tilde coordinate x and untilde x. Physically, the two-fold local Lorentz symmetries, or the two spin groups, indicate that there are two distinct locally inertial frames for the left moving and the right moving closed string sector separately. And this immediately implies the unification of 2A and 2B. So each spin group has its own supersymmetric double field theory is unique theory, but it turns out to contain two different types of solutions, namely 2A and 2B. This page shows what are the fundamental fields in double field theory, namely closed string matrix sector as string graviton fields. So they consist of the DFT dilaton, denoted by small d here, and DFT metric calligraphic H. It's often called also generalized metric in the literature, and it satisfies two defining properties, symmetric and ODD element. Combining ODD invariant metric J and H, one can construct a symmetric projection matrices, P and P bar. P square is P, P bar square is P bar. They are orthogonal and complete. Further, taking the square root of the projectors, P equal V square, P bar equal V bar square, we get a pair of DFT field binds, V and V bar. So V square contracting capital letters is eta, V bar square is eta bar, V bar orthogonal and complete in this sense. So double field theory or string gravity works with the fields DH in the bosonic case or the V and V bar in the Fierbein formalism without referring to the Riemannian variable GB phi. Then one can ask what is the most general solution to these two defining properties. So with Kevin Moran, we obtained the classification of the most general form of the DFT metric satisfying these two properties. It turns out to be characterized by two non-negative integers, n and m bar. So what we did is that take the generalized metric, focus on this d by d block, which we call capital H, and we classify any possible degeneracy over this d by d block. So basically, n plus m bar is the dimension of the kernel of this d by d matrix H. So here, H and K are symmetric, and we have again NS and SB field here. It turns out that H or K admit two different kinds of the eigenvectors having zero eigenvalue. One is x and the other is x bar. So x, the index I runs from 1 to n, and there are n of them, and then I bar runs from 1 to m bar. And same for k. We have y, zero eigenvectors. They satisfy certain completeness relations. And from this, orthonormality relation follows. It is instructive to note the ODD invariant trace given by 2 times n minus m bar. So this remains invariant under any T-duality rotations. And also note that B field acts in this order-joint manner. So it's clearly when n bar is trivial or 0, 0, this corresponds to the well-known Riemannian parameterization of the generalized metric. Or in the Fierbein formulation, which I don't show in detail here, it gives the, what is known as generalized geometry a la Hitchin. Then generically for non-trivial n, m bar, as I will show in next slides, string becomes automatically chiral over the n dimensions and anti-chiral over the m bar dimensions. I call such a background, non-trivial n, m bar, as a non-Riemannian geometry because what should be the inverse of the Riemannian metric is now degenerate. So you cannot associate any Riemannian metric even locally. So such non-Riemannian examples include 1,0 Newton Cartan gravity. If you remember Tuesday, Niels Bohr's talk, this zero eigenvector x is nothing but what he calls absolute time. 1,1 turns out to correspond to the Gomez-Oguri non-relativistic string. In fact, with the two local organizers, Charles and Lune, we saw that the fluctuation around this 1,1 background in double field theory matches the spectrum of the Gomez-Oguri non-relativistic string. Further, the isometry group forms the Bergman algebra. We can have also ultra-relativistic Carroll gravity. One intuitive way to see that the y 1,0 corresponds to the non-relativistic limit is if we consider the flat Minkowskian metric with the expressed appearance of the speed of light. If you take large C limit, of course metric blows up, it's singular, but the inverse of metric, which should appear here, now remains finite but degenerate as 1,0. So in this way, singular geometry in GR can be smooth in double field theory. And their dynamics will be all governed by the Einstein double field equations. Diffeomorphisms in strings gravity are given by what so-called generalized Lie derivative by Siegel. So we have the usual transport term, any possible weight term, and then we have the local ODD infinitesimal rotation for each index. And for consistence, the so-called section condition should be imposed. So this is the rule of the game in double field theory that whenever you see the contraction of the derivative indices, they are supposed to vanish. So from this explicit expression, we note that the section condition can be easily solved by letting, for example, all the fields are independent of the tilde coordinate. The general solutions are then generated by the global ODD rotation of this particular solution. I know the section condition is actually the source of many complaints from outside of the double field theory community. But what is mathematically true is that the section condition is equivalent to a certain translational invariance. So here capital phi I, phi j, phi k are just arbitrary functions which appear in double field theory. So it includes d, h, and any gauge parameter and their arbitrary derivatives. And delta m, because this vector index can be identified as the this derivative index, where the index is also raised by ODD invariant metric, this delta m is said to be derivative index valued for obvious reasons. And if you consider any Taylor expansion of this, you can show easily that they are actually equivalent. So this suggests, this let me suggest to think that physics should be invariant under such shift of the doubled coordinates in double field theory or in strings gravity. So with some technical motivation, which I don't talk here, I propose that the doubled coordinate in double field theory are actually gauged through an equivalence relation, where this delta m is a derivative index valued I mentioned. So each equivalent class or gauge orbit in doubled coordinate space now corresponds to a single physical point in R to the D. So if we solve the section condition by letting all the fields are independent of tilde coordinate, then you can easily show that indeed tilde coordinate is gauged, but untilde coordinate remains as the physical coordinates. Then the ODD rotates the gauge direction, and hence the section is also rotated. Further, if we gauge this infinitesimal one form explicitly by introducing a derivative index value gauge potential, so it should satisfy this relation, then it is possible to define ODD and double field theory differentiation covariant proper length in this double yet gauge space-time through a path integral. So it's also easy to show that if we plug the 0,0 Riemannian DFT metric into this expression, then after integrating our auxiliary gauge potential, this definition of the proper length reduced to the conventional one in Riemannian geometry. And since it is independent of tilde coordinate, indeed measures the distance between the two gauge orbits, which is of course a desired property. So this definition of the proper length immediately generalized to the covariant action, particle action and string action in this Polyakov formulation. So again, with the 0,0 Riemannian DFT metric plot, these ODD manifest double gauge signal model all reduced to the conventional point particle action or the string action, plus some total derivative where you can see still tilde coordinate here. This also extends to the kappa symmetric Green-Subaru superstring. And thanks to the twofold spin group, it also unifies 2A and 2B. So what about generic n, m bar background? So we are going to plug generic n, m bar background into this sigma model. Then it's useful to note that the auxiliary gauge potential decomposed into three pieces using the completeness relation of the KH, XY, X bar, Y bar. So the first one appears in the Lagrangian quadratically, and which leads to the Gaussian integral, as in the Riemannian case. However, this second and third term appears linearly, and this plays the role of the Lagrangian multipliers. So it prescribes in the dynamic such that particles just completely frozen over the n plus m bar dimensions like this. And then the remaining orthogonal directions are described by this reduced action where you have the degenerate, let's say, metric K. If you do the same game with the string action, string becomes now automatically chiral over the n dimensions and antichiral over the m bar dimensions. And this string action reduced to this bosonic undoubled theory, where the G mu nu is replaced by K mu nu, like in point particle case. Now let me move to the definition of the covariant derivatives and curvature in strings gravity, which turn out to feature two stages. One is semi-covariance, and second is its complete covariantization. So covariant derivative or semi-covariant derivative can be written down like this with possible weight term here with the introduction of the string theory extension of Christopher connection, gamma here. So gamma can be uniquely fixed by demanding the compatibility with the projectors as well as dilaton D, and for the some torsionless conditions. One remark is that there are no normal coordinates where the gamma connection would vanish pointwise. So, in other words, equivalence principle is broken for string, i.e. extended object. But it's recoverable when whole formalism coupled to point particle, because you will only the metric or the string framed Riemannian metric coupled to the particle. One can define also the four-index Riemann curvature out of this connection gamma, and one crucial property is that on the infinitesimal transformation, it varies like a total derivative with respect to this connection covariant derivative. To take care of the two spin groups, one can also introduce two spin connection, phi and phi bar, and this can be also fixed in terms of this Christopher connection by demanding the compatibility with the DFT Fierbein. Okay. Now, our covariant derivative is semi-covariant in the sense that they are not automatically covariant on the diffeomorphism. However, after projecting the indices properly, they become completely covariant. We have the completely covariant derivative. So this arrow denotes the contraction with the Fierbein. So you can see the structure more easily. That derivative index is unbarred and tensor index is all barred, or the opposite case. We have the divergence as well as Laplacians. And this formalism extended to the Dirac, covariant Dirac fermion as well as the RI sector, where the whole Lamont sector is represented by a single field which is bispinorial. Sorry, yeah. Okay, yeah, no problem. I can finish. Okay, and then finally we can also construct a completely covariant two-index Ricci curvature and scalar curvature. So they after plugging the 0,0 Riemannian background reduced to the well-known generalized geometry result or the so-called H-twisted K-theory extra derivative or the democratic Lamont formulation. And the scalar curvature gives the aforementioned closed string effective action. And the formalism was used to construct a maximally supersymmetric double field theory, which unifies 2A and 2B supergroup, as I mentioned, thanks to the two-fold spin group, where one can couple it to the four-dimensional standard model, just like how Einstein gravity couples to the standard model. So now, in the remaining 3 minutes, I will present the derivation of the Einstein double field equation. So let me consider a generic action for strings gravity coupled to matter field epsilon here, where the S0 is this scalar curvature and matter Lagrangian is equipped with our completely covariantized master derivative. And then we consider the generic variation for each term, and then while you vary the matter part, you have we are naturally led to define two quantities, K and T0, for the Fierbein V and or the dilaton D, just like as a counterpart to the Ricci curvature and scalar curvature. So this result, combining them, we have the equation motion for the whole Lagrangian. This is the equation motion for the matter, the Euler-Lagrangian. We have these two equations. And these two will be, in the next slide, unified to the Einstein double field equation. For this, we consider further, the variation is all given by diffeomorphism. And what I'm doing here is the standard prescription in usual GR. If we consider the general covariance of the action, we have a certain identity where the natural definition of the Einstein curvature as well as strings energy momentum tensor appear. This is the divergence of these quantities. So they are off-cell conserved or the on-cell conserved because of this extra Euler-Lagrangian equation. So since this Einstein curvature and energy momentum tensor each have this tier plus one component, and they can be decomposed by the contraction with the V or taking trace, the older equation motion of the closed string sector, Messerly sector, or the DFT Fierbein and dilaton can be unified into this single expression, which is manifestly ODD invariant. And it is naturally consistent with the central idea that strings gravity treats the entire closed string Messerly sector as a geometrical strings graviton field. So, to illustrate, if we restrict to the 0,0 Riemannian background, this single equation decomposed into these three equations. So one is the equation motion for the metric, B field, and then dilaton. And for other non-Riemannian cases, the equation should also describe the dynamics of the chiral gravities I mentioned earlier. So there are some examples for each cases, but I will skip this and then let me conclude. So string theory may predict its own gravity, namely string's gravity rather than GR. String's gravity also may be formulated in this double yet gauge space-time and unifies Riemannian supergravity and non-Riemannian gravities, such as Newton-Cartan, Carroll, or Gomis-Oghri. And deserves further exploration, for example, the ODD covariant holographic dual of string's gravity. So thank you for your attention.
Are there any questions?
So when we talk about holography, the basis that there is much of global symmetries in ADS and in the CFT. So your question somehow provokes, like, it seems like you are saying that ODD is a global symmetry in your theory.
Yes, it's the most important built-in symmetry from the beginning. Yeah.
I mean, it is not realized linearly, right? ODD.
It's linearized in this DFT ODD covariant variable like generalized metric and dilaton. It's singly. But in terms of GB phi, it's like a Gaussian rule, basically, non-linear.
Okay, maybe we can discuss later.
Let's see, we now understand strings a little bit better since there is the duality with Young-Mills. And since one has ADS-CFT duality with Young-Mills theory, the n equal 4 super Young-Mills. Yeah. So does that explain this double field theory? Winding modes are kind of very natural in Young-Mills theory. So is there any indication that this ADS-CFT duality would explain the structure which you are using and Zwiebach is using?
It's a very good question, but
is there any indication, a small one, not a derivation, but just maybe just an indication?
From the
Young-Mills,
side,
yes.
So Yang-Mills theory itself can be written ODD covariant manner. That I just skipped, but
no, we don't want to change Young-Mills.
Without boundary, without changing, one can rewrite as if it's the ODD covariant manner.
Okay.
Without any deformation.
Okay, so I think we should move on, and thank you, John, very much again.